Hi, my name's Shaked and I'm one of the developers for a game called Prickle, a cute puzzle game about hedgehogs which is now on Steam. But today I want to talk about distortion and reflection shaders. As you can see, in Prickle we have some water, but the game is in black and white, so it's pretty hard to convey that this is water without coloring it blue. So what we did, we used a reflection and distortion shader, and specifically something that looks like water waves or water ripples. And that's what I want to talk about today and teach you how to do. Now, before we even begin, I just want to say that there are a lot of really good Godot water shader tutorials here on YouTube. And if you're just looking to get the best result in the shortest amount of time, you should watch one of those. But the purpose of this tutorial is to give you a fundamental understanding of shaders and how to use the building blocks that you'll find in almost every shader that you're gonna write. So this is going to be a very in-depth explanation, so you'll understand exactly what you're doing in every step of the way. So let's start. By the way, if this is your very first shader, I do recommend that you watch my introduction to shaders video before, where I explain about the very fundamental basics of shaders, and then you can watch this one. So the topics that we're going to discuss today are UV and screen UV and what's the difference between them, how to sample a texture using an offset, how to use the sine function and why do we use it, how do we use the time parameter with the sine function, how to sample a noise texture, and at the end of the tutorial we'll talk about zoom and scale and how to account for them. So let's start by dragging the Godot icon to our project and apply a shader material to it. Let's call it a ripple reflections or something like that. And in this tutorial, I'm going to talk only about the fragment part of the shader, so I'm deleting anything else. Now, the first thing I want to talk about is UV coordinates. Now, every sprite has a starting point, and in Godot, this starting point is on the upper left corner. And when we want to talk about the coordinates of this corner, we'll say it's 0, 0, the starting point. And then we'll talk about other coordinates, like a percentage of the sprite. And what do I mean by that? If we look at the x-axis, we'll see that if this is the starting point, this is the ending point, which means 100% of the sprite. So if this will be 0, 0, this point will be 100% and 0. Instead of 100%, I'm just saying 1 and 0. So this point will be 0.5 and 0. So 0.5 on the x-axis, but 0 on the y-axis. And if we look at this point, it will of course be 0 on the x-axis and then 0.5 on the y-axis and so on. So this point will be 1, 1, which means 100% of the x-axis and 100% of the y-axis. Let's see a demonstration of this principle. In order to get a good visual representation of the sprite's UV coordinates, I want to color every pixel in the sprite according to its UV coordinates. So first of all, I just want to color everything black. So I'll do color point RGB equal to vector 3 of 0.0. And then let's say the color point A is always 1.0. And now we have a black square. And now, what I want to do is just to color only the red values according to UV. I'm just writing UV and it's automatically gonna be the UV of the sprite I'm working on right now. And then I'm gonna say the X value. And now we can see that the left part of the sprite will have 0 redness because this part is the X value is going to be 0, and on this part it's going to be 100%, like 1. And if we'll stretch the sprite, we'll see that it remains the same, like the most left part will be always 0 and the most right part will be always 100%. And even if I'll like change the camera and I'll zoom in or out, this will always remain the same. You'll understand in a bit why I'm like so focused on this part. Now I want you to do a small exercise. I want you to pause the video and then create a similar shader, but for the y-axis. I want you to go for each fragment and change the green value of the fragment according to its UV coordinates, but only for the y-axis. So pause the video, try to do it yourself, and come back here. So I hope everything went okay and it was really easy, but just in case, let's do it together. So I want to change the green value for every fragment according to the UV on the y-axis. And if we look at that, oh, that's exactly what we wanted. We see the upper part is totally black because it's 0 greenness, and the lower part is 100% green, and everything in the middle is shades of green according to the coordinates. And what will happen if we'll add both of these together, we'll get something that is usually how we represent a UV map, using the color red, green, and when they are combined together, yellow. So if you'll see something like that, that's what it means. It's just a UV map. Now let's talk about screen UV. Now screen UV is very similar in principle to the sprite's UV, but instead of for the sprite, it's for the screen. So this point will be 0, 0, and if I'll move around, this point will be 0, 0, because this is now the upper left point of the screen, and this point will always be 1, 1, and if I'll change the size or resolution of the screen, now this point is going to be 1, 1. So the zoom and camera movement and screen resolution are all going to affect the screen UV. Let's see a visual representation of that. Let's do the exact same thing, but now let's color it, instead of UV, let's call it screen UV. And I'm commenting out the y-axis. So now, if I'll move around the screen, we'll see that now I'm not moving the actual sprite, I'm just moving around the screen, and now we can see that when the camera pans and to the right part and the sprite is in the left part of the screen, it turns black because the UV values here are 0. And if I'll just go here, the square will turn red. The same thing will happen if I'll zoom out. You can see that if I'll just move the square around, it will get colored according to the x-axis of the screen. And it also means that if I'll change the size of the screen, you can see that the square is going to change color. So this is what screen UV means, and of course it goes both ways. I can change the color according to the screen UV on the y-axis, and we'll get a similar result. So that's screen UV and UV, and I hope the difference between them is very clear. Another difference that I want to state is something that's going to be really important towards the end of this tutorial. So if I'll show the X and Y values using a UV map, you see that if I'll squeeze or stretch the sprite, it's not gonna squeeze or stretch the texture. It's just gonna show different parts of the screen UV. But if I'll use normal UV or just like the sprite's UV, then if I'll try to squeeze the sprite, the texture will get squeezed or stretched as well. And this is really important for some shaders. Now, when we have a better understanding of UV and screen UV, we can start making our shader. So first, let's cover the entire screen. I will change the Z index value until it covers everything. And now let's change our shader so it will sample the screen. I've talked about it in my previous video, my introduction to shaders video, so I'll do it really quickly. And here I'm going to do color equals texture of screen texture at screen UV. And now every pixel on our sprite will be the same as the pixel on the screen below it at the exact location of the pixels that we are working on. So like a chameleon, it will change the color of the pixels according to the pixels of the screen below it. But now I'm asking myself, what will happen if I'll use a different value than the exact screen UV coordinates of the pixel that I'm currently working on? For example, let's imagine I'm currently working on the central pixel on the screen. So the screen UV coordinates will be 0.5, 0.5. It will be somewhere around here. And what it does currently is just going to the screen and going for the exact same location and taking the color from there. But now, if I'll change the screen UV, I can tell it, hey, color this pixel according to that location. So how do I do that? And let's see what happens. If instead of going to the screen UV, I'll just say screen UV and a little bit more to the right. So let's add a vector 2, but I'm only gonna change the x-axis. And I'm going to use really small values because I remind you that the entire screen is 1. That's 100% of the screen. So let's say 0.01, and then I'm going to leave the y-axis exactly the same. So let's see what's gonna happen. Now, when we sample to the right point, it will actually move our entire screen to the left when we use the shader. So that's the original, and that's what's under the shader. And what's cool is we can change this value how much we want. If we'll change it like to 2, it will move a little bit more, and to 3, a little bit more. And if it will be negative, it will go to the other direction. So that's pretty neat. Let's visualize this even more using a uniform. So if I'll create a uniform, let's call it x offset, and let's use a hint range, and it will be from a negative, let's say a negative 0.5 to a positive 0.5 and skips of 0.01. So now if we'll go to the shader parameter, semicolon, if we'll go to the shader parameter and we'll play with this, nothing will happen because we need to assign it here. And now we can see that when we change the X offset, it will actually change how we see the screen. So our next step when we want to create distortion is we want to create something like this that moves around, but we want it to happen automatically. I don't want to change this value manually, right? So to do that, I need to have a better understanding of the sine function. This is the sine function. Now, I really don't want to get into the math behind it or talk about what it actually represents. What I really want you to focus on is the fact that we start with a sine of 0, which is 0, and then in skips of 90, we go to 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on to infinity. So if we start with a sine of 0, which is 0, a sine of 90 will be 1, a sine of 180 will be 0 again, and then a sine of 270 will be minus 1, and then 360 will be 0 again. But the important part, and probably the most important part, is it doesn't matter where we start. If we start on 360, we add 90, we get 1, we add another 90, we get 0, add another 90, minus 1, we add another 90, we get 0. And we can start here, or actually anywhere we want. We can go to like millions or hundreds of thousands, and it will still remain exactly the same. We start here on 0, we add 90, we get to 1, we add 90, we have 0, we add 90, we have minus 1, and so on. So why is that so helpful? To better understand, let's first remember the x offset float that we created before. If I'll add more value to it, at some point it will just go beyond the limits of the screen. And then it doesn't matter if I'll add more and more and more value to it, it just doesn't change anything, right? But the sine function works differently. And let me explain what I mean by that. So if I'll create a float called the sine offset, and then I'll assign it here instead of the x offset, right now it equals 0, and let's say it's a sine of 0. And before I move on with this demonstration, I just want to say that the sine function here is in radians. So instead of degrees like 90, 180, or 360, it's in radians like multiplications of pi. So just to make it a little bit more intuitive, I'm going to convert from radians from degrees to radians, so it will be simpler for us. So let's say float radians is converting, let's say right now 0. So this value, let's make a uniform. Sorry if it's a little bit all over the place, but it will all make tons of sense in a moment. Let's call it degrees, and let's make even a hint from 0 to 1000. Yeah, something like that. Okay. So what we're going to do is to convert from this uniform to radians. This is going to be in degrees. We'll convert it to radians, and from radians to the sine function. So now let's see what happens if we'll add more and more value to the degrees uniform. I'm adding value and it does leave the screen, right? But then if I'll add more value, it will come back. And then I'll add more value, it goes to the other side. I remind you, that side is 1 and that will be -1. And it will go back. And then we can go over and over again. And it doesn't matter if I'll add a lot of value to it, it will always go in the same way. 1 and -1. And if I just want to demonstrate it in just a little more visible and like sensible way, I can just, instead of 1 and -1, which I remind you, 1 is the entire screen, I just want to like multiply it by something like 0.1. And now you can really see that it goes to both directions, and I can add more and more value and it will remain the same. So that's really important. Now we understand the sine function way better, but it still didn't solve the problem we faced earlier, which I'll remind you is how to change a parameter automatically. Because right now, yeah, instead of just taking it back and forth, I can add more and more value to it, but I still need to change it manually, right? So instead, I need to think of a parameter that automatically keeps going up and up to add more and more value constantly, no matter what. And I can think only of one parameter like this, which is time. I can actually count the number of seconds that passed since I've started the engine and use it as a parameter in my shader. And it's actually one of the most useful parameters that you can use in shaders. Let me demonstrate. If instead of degrees, I will just write the word time in uppercase, it will automatically use the number of seconds that passed since I've started the engine. And you can see that, yeah, it moves automatically, but really, really slowly. And I'll remind you why. Because we are using the sine function, and to complete a full circle, it needs to go from 0 to 360. And if that's seconds, it will take 360 seconds, which means 6 minutes to complete a full circle. So let's speed it up a little bit. I can just multiply this value, let's say by 200. And let's see what happens. Oh, and now it moves way quicker. So if I want to speed up or slow down something, I can just multiply the time value by something bigger or smaller than 1. So now let's add 2 uniforms just to make things a little bit more clear. As we can see, we have 2 multipliers right here. We have the time multiplier, and if we'll change it, things will move slowly. It will still be at the same amount, so it will get here, but just slowly. Let's try it out, and we can see the movement is slower, but the amount is the same. And then we have the other multiplier. It's after the sine function. So I'll remind you that a sine function moves between -1 to 1. But if I'll multiply it by 0.1, it will move between minus 0.1 to positive 0.1. So if I'll change this parameter, it will affect the amount of movement. It will stay in the same speed, but the amount will be different. Now, it looks faster, but the cycle speed remains the same. The frequency remains the same. And if I want it faster, I can always change the time multiplier. So let's create 2 uniforms to represent that. I'll create a uniform that I'll call speed. And let's use a hint because it's always more convenient. Let's say from 0 to 500. And let's create another uniform that we'll call amount. And that will be from, let's say, 0 to 0.5. And it will be in way smaller steps. And now, of course, let's assign them instead of these multipliers. Yeah, and now we can control the amount and speed of the movement. And I know it still isn't like a water distortion shader, but we're going in the right direction. The problem here is when we think about how water moves, it doesn't move as one block left and right, left and right. I mean, every little part of the water moves in a slightly different direction, and that's what makes the ripple effect so unique. So I'm asking myself, which parameter do I know that's a little bit different for every pixel in the sprite? And I think if you'd ask yourself the same question, we'll both come up with the same answer, which is the UV coordinate value. So we know that for every pixel, there's a different UV coordinate value. So if we're talking only about the y-axis, here it will be 0, and here it will be like 0.5, and here it will be 1. So what will happen if I want the amount, for example, to be affected by the UV coordinate on the y-axis? So I can just multiply the amount in the UV value on the y-axis. So I'm writing UV.y, and now here it will be multiplied by almost 0. If I'll take it here, it will be completely 0, right? And now we have 0 movement here, but here we get almost the full motion. Let's do it like exactly 100% of the motion, and we get all the in-betweens. And I know it's not exactly what we wanted, but still every pixel moves a little bit differently, so that's good. So let's stop and think for a moment about what is it exactly that we're trying to achieve, because right now we are controlling the amount of movement that every row of pixel has. So the top row has no movement at all, and the bottom row has 100% of the movement. But is it really the amount of movement that we are trying to control? I mean, if I think about the wavy motion that we're trying to achieve, and if I look at my hands, you can see that the top row moves and the bottom row moves, and they all move at the same amount, but just at a slight delay. So let's think, how can we do that? Now that we've decided that we don't really want to change the amount of movement for every pixel, I can remove this part of the code. And now, all of the pixels will move at the exact same amount at the exact same time. And what I'm thinking about right now is how can I introduce a slight delay to the movement of every row of pixels according to its UV coordinates on the y-axis. And my intuition tells me that if when we try to change the amount of movement, we multiplied it by the UV value, we can do the same with the speed. So let's try it and see what happens. Let's multiply it by UV.y. Oh, so that doesn't look exactly how I expected it to look, right? And it's really unpredictable and really chaotic. So let's understand what exactly is going on here. So one of my methods when I'm just trying to figure out what exactly is going on is to replace the UV coordinates with a specific single value in the UV range. So I know what exactly is going on in every row of pixels. So for example, if I want to know what's going on at the top row, I want to input here the value of the UV coordinates at the top row, which in this case will be 0, right? So let's see what's happening at the top row. Oh, practically nothing. And it makes sense, right? When you multiply everything by 0, you get 0. So it's not exactly what we wanted, but let's see what's happening at the bottom row, right? When you multiply everything by 1, you get, oh, the same value. Still no surprises, right? The exact same movement as we had before. But the interesting part is what's happening in the middle. For example, when I'll input 0.5. So I can see it's the exact same amount of movement, but the frequency is halved. So it's way slower. And it's some kind of what we wanted, but let's imagine we get closer to 0, right? And we have something like 0.1 in these rows, some like more or less. So now see how slow the movement is. And that's not at all what we wanted, right? We want the frequency to remain the same, but to just have a slight delay for every row of pixels. So now when we have something like, let's say 0.01, we have almost no movement at all. And right now, every row of pixels moves at a different frequency. and not just with a slight delay. So this is why when we do uv.y, we can see every row of pixels moving in a different frequency. So what can we do otherwise? So we understand that if we multiply the speed by the UV value, we get a different speed for every row of pixels. But that's not what we want. We want to add a different delay to every row of pixels. So let's focus on the word add. And let's understand what happens if we add values here. So let me just remind you that we're thinking in degrees here. So let's try to add something like 90 degrees and see what's gonna happen. Oh! So it started from a different location, but it went back to doing the exact same movement. So it's the same amount and the same frequency, but it just started from a different place. Let's try a different value, like 180. Oh, so it did the exact same thing. So now I'm thinking, what will happen if for every row of pixels, I will add a different amount of delay? So for the top row, it will have 0 delay, and it will mean it will go in the exact same frequency and the exact same amount. But for example, let's say the bottom row here will be at a 90 degrees delay. So it will start at a different place, but it will still do the same amount. So let's just multiply that by the UV coordinates and see what happens. Ooh, that's more like it. So we have a slight delay of 90 degrees. What will happen if I'll try like a different amount, like 180 degrees? Oh, so that's nice. We have a bigger delay, so we have more movement. So what will happen if I'll change the value of this multiplier to something smaller, like 30 degrees? So we can see that there's still a difference between the top row and the bottom row, but it's a smaller difference. It's a 30-degree difference. So if I'll make this multiplier bigger, the difference between the top row and the bottom row will get bigger. So let's try 360, and now we have a bigger difference. And if I'll try something even bigger, like 720, we have a lot of difference. So we can actually make this multiplier be the frequency of the wave, not the frequency of the motion, that's the speed. I'm talking about how many waves do we have here. So let's make another uniform. And let's call it frequency. And it will be, of course, a hint, but because we're thinking in degrees, it will be between 0 and, let's say, 1000. Yeah, something like that. I think it will go well. So let's just assign it instead of this. And now, when we go to the shader parameters, we can change the frequency, and that's really beautiful. Now the amount is way too big, so let's take the amount a little bit down, and that's starting to look like a water shader. And of course, we can play around with the parameter to change the speed or to have something really small, but with more amount. We can play with it and make it however we want it. That already looks pretty good, but I think it's not good enough, because the problem with a sine wave is it's really predictable and really repetitive. So I know that a sine wave always goes to 1, 0, minus 1, 0 at the exact same frequency and the exact same time to infinity. So when I look at the texture distortion here, I know exactly what's going to happen. The pixels are going to move left and right at the exact same frequency. When it becomes predictable, it's not exactly like a body of water where the ripples are really chaotic and you can't really predict where they're gonna go, right? One of the solutions to this problem is to create another sine wave with a different frequency and multiply these two together. Now, that's not the solution I'm gonna go with in this tutorial, but I just want to demonstrate to show you how it looks like. So let's say here instead one sine wave, I'll create another one. And right now it's the same frequency. Let's say it will be, I don't know, let's multiply it by some amount, and you can see it's still a sine wave, but it's less predictable, and the amount currently is changing a bit more randomly. So that's nice, but that's not what I'm gonna go with. What I wanna do in this tutorial is change the offset value for each pixel based on a noise texture. Now, what is a noise texture? The best way to understand it is to see it for yourself, and the best way to see it for yourself is to create one. So let's understand how to create a noise texture. So first of all, I'm gonna go to the uniform part of the code and just add another uniform. It's gonna be a sampler 2D, which is basically any kind of 2D texture, and I'm gonna call it noise, and I'm done here. And now when we look at the parameter, we can see we have another parameter called noise, and when I click here, it will ask me what kind of texture do you want, and the answer is of course a noise texture. And if I'll click here, we still have no texture here, so we need to go to noise and to pick a new fast noise light, and that's a noise texture. So a noise texture is what seems to be a randomly generated pattern of black and white value. It is actually not really random, it is generated off of a seed, and if I'll give it the same seed, it will always create the same pattern. So you can even change the seed here if you want, but that's not really the important part of the video. You can try new noise patterns and new frequencies and values, but actually if you'll just go with the default, it will look just fine. So if we'll manage to change the amount of offset for every pixel according to the amount of whiteness in every pixel in the noise texture, we'll get something that will look really random, and that's exactly what we're going for. Our next step is to sample the noise texture. Now, we already do know how to do it, right? Let me remind you that we already did it with the screen texture. We use the texture function, which samples a specific point at this texture at this location. So we can do the same thing to sample the noise texture. Let me demonstrate. I'll comment out everything here, and let's create a new shader that's gonna color every pixel in the sprite according to the pixel at the center of the noise texture. So let's do that. Color equals texture, which texture, the noise texture, and which location, vector2 of 0.5. To make it a little bit more readable, we can even do 0.5, 0.5. And now we have a specific shade of gray that is right in the middle of the noise texture, and if I'll change the values of, let's say, the X value, you'll have a different pixel, which is right about here, and it's a different shade of gray. But what if I want every pixel in the sprite to have a different value according to its UV coordinates? So for example, if I'm working on the pixel in 0, 0, I'll go to the noise texture and sample at 0, 0. If I'm working on a pixel at 0.5, 0.5, I'll go to the noise texture and sample at exactly 0.5, 0.5, and you get the idea. So I think you're familiar with the idea of sampling at the UV coordinate location, and we can do it here. Instead of just one coordinate, I'll just tell it to go to the UV coordinates of the pixel that you're currently working on. So let's just write UV, and we've sampled a noise texture. Now I want to take the white value of each pixel and use it to determine the amount of offset for this pixel. Now, how can we know the amount of whiteness that every pixel has? Well, it's pretty easy. I can just check for the amount of redness or blueness or greenness, because they are all going to be equal to each other because the noise texture is black and white. So in black and white, the red, green, and blue values are all the same, and they will be equal to the amount of white in the pixel. So if I want to create a float, let's call it white value, it will be equal to the color of the pixel, but we'll take only the red value, which will be the amount of white in the pixel. Now we need to rewrite our code a little bit. So what we need to do is first bring these lines back in and comment out these lines, and we're back with our sine wave ripple shader. So let's change the name of this float to just offset, because I don't want to get confused. And I'm just gonna remove this entire line because we don't really need it, because we're not going to use sine of radians anymore. What we're going to use instead is this, the white value, because we're changing the amount of offset according to the white value. So let's do just white value of the noise texture and multiply it by the amount of distortion. And now, if we'll change the amount, you can see that the distortion is way less predictable and repeatable than the sine wave. It's really random-like, and that's exactly what we wanted. But now I have a different problem. Our ripples don't really move. And I know I should probably add some value somewhere, or I don't know, use the time parameter, but where and how? So let's do some testing and figure that out. First thing, I'm gonna bring back this line, which basically cancels out everything we did before and just sets the color of every pixel according to its UV location on the noise texture. So now I can visualize the noise texture better. And I'm asking myself, how can I make the texture go to the left or to the right? And I remember that something that at the beginning of the tutorial happened naturally when we had an offset. So let's try to add an offset only on the x-axis. So I'm creating a vector 2, and let's say 0.1 on the x-axis and 0 on the y-axis. And yeah, it moves a little bit. Let's try to add some more value here. Yeah, every time I'm adding some value, it moves the texture, and that's really good. But at some point, as you can see, I'm just running out of texture because the texture is not infinite like the sine function. So what can I do? I have a secret trick. If I'll go to the uniform, I can just add a hint and write repeat enable. And now the texture will repeat itself once it's running out of texture. And that's really good, but we can all see the huge seam that we have that connects both texture and the repeated texture. So what can I do to get rid of the seam? Well, it's another secret trick. I'm going to the noise uniform and I'm just ticking the seamless box. And now the noise is infinite and seamless. So now we want to make the texture constantly go to the left. Now, I know that if I'll just keep adding more and more value here, I know that it will just keep going to the left. So I want you to do another little exercise. Pause the video and try to come up with a way that the texture will constantly go to the left all the time. So hopefully you paused the video and you figured out everything on your own, but just in case, I'm gonna explain anyway. So I know that this X value, I want it to go up and up in value constantly all the time. So I know just one parameter that does exactly that, which is of course the time parameter. So if I'll write time here, now exactly like we wanted, the texture goes to the left constantly, but I do want to control its speed. So yeah, that's supposed to be pretty easy. I'll just multiply it by our speed uniform, right? So let's do that. And yeah, now it's crazy fast because right now our speed uniform, which before was divided by 360, now we just multiplied the speed by 250. So we can change the values of the speed uniform, but I think a simpler way will just be to divide everything by, let's say, 200. And now, yeah, everything makes tons more sense. So when it's here, like 40, it's still really slow, and when it's fast, it's fast. So I think it's a pretty decent way. Now we have just one thing left to do, which is to comment out this line. And when we check for the white value of a pixel, instead of checking for just one UV value, let's add the offset that we had before. And like magic, now our noise generated ripples are moving. And that's basically it. There are a few tweaks that we can do to make our shader better. So first and foremost, we can see that we add the offset only to the x-axis. So lines like these remain straight because they are not distorted on the y-axis, which is kind of weird. So first of all, we can just apply the offset on the y-axis as well, which will improve the general look. But I do want more control of the amount of distortion on the X and Y axis, so I'll just add two uniforms. Let's add a uniform. Let's say it's a float. Let's call it X amount. And yeah, let's add a hint like that. And we'll do the exact same thing for the Y amount. And now we can just multiply the offset in X amount and Y amount. And now we have these two parameters that control the amount of offset on every axis. So if I just want a little bit of distortion on the y-axis, I can just add this or just remove almost all of the distortion on the x-axis, which is kind of nice. Another thing we should probably do is to make sure our shader is as clear and readable as possible. So if I'm gonna leave it for like half a year and then come back, I'm not gonna remember anything that I've done. So it's really important that the shader will be self-explanatory and will be easy to understand even if I don't remember what I did though. So for example, let's take this part. I think we can simplify it a little bit more if I'll just create a vector 2 and I'll call it the offset vector. And then it will be equal to the offset and I will multiply it by the x and y like I did before. And here I will just say screen UV plus the offset vector, which I think is way clearer. And of course, comments are really welcome and you should write to future you to explain what you just did. Now, if your game is not in black and white, which is probably the case, I suppose you'd want to color the water in some shade of blue or green or whatever. So let's add a new uniform and we'll color our shader with that color. So it's gonna be vector, let's say 4, and we'll call it tint. And we'll use the source color hint. And now let's just pick a color and let it be blue. And now if we'll just make the color blue, then obviously what's gonna happen is, yeah, we're just gonna color the entire sprite blue. So what we're doing instead is just mixing the two values. So color equals mix of the current color and tint, and we'll mix it by, let's say, 0.2 and semicolon. And now our water have a slight tint to it. If I want the tint to be stronger, I can do it up to like 50%. And now I can change here the amount of blueness. And yeah, it looks pretty good. Now I want to address two problems that you might have noticed. The first one is pretty easy to solve and it's relevant only to this shader, but the other one is extremely important to your understanding of shaders in general, and it will be relevant to almost every shader that you're gonna write. Our first simple problem is that our offset is only positive, which means it only goes to one side. Let me demonstrate. I'll remove the Y offset and let's bring up the amount of offset on the x-axis, and especially if I look at the texture below, we can see that our distortion only goes to the left. We don't have any distortion to the other side. And the reason is that our offset is based off of the white value, which is between 0 and 1, and it's multiplied by the amount. So this minimum value will be 0 and the maximum value will be 0.5. So I want to subtract the value here, so it will go below 0. Now the problem is, if I'll just subtract the amount, we'll have the exact opposite problem. Now when this is 0, then that will be minus 0.5, and when this is at the maximum value of 0.5, it will be reduced to 0. So then it will only go to the right. So if I'll subtract the amount and I'll divide it by 2, now it's going to both sides, which is what I wanted. The bigger problem is what happens when I try to stretch or squish the sprite. So if I'll try to stretch it, you can see that the ripples are changing shapes. They are becoming stretched or squished as well. And that is because the noise texture is based off of the UV coordinates. And I'll remind you that at the beginning of the tutorial, we spoke about how when you stretch or squish a sprite, the UV coordinates get squished as well. So you might be thinking, why don't I use the screen UV instead? Because I know that even when I squish or stretch the sprite, the screen will remain the same size. So let's try it out. We'll replace the UV with screen UV. And now, if I'll squish the sprite, the ripples remain at the exact same proportions, which is really good. But what will happen if, for example, I'll zoom out? Let's look at what's happening to our ripples. They are getting crazy big, and if I'll zoom in, they are getting crazy small. And that's because the screen, even when I zoom in or out, the screen remains the same. So the sprite becomes smaller, but the size of the ripples stays the same. One other very common problem with using the screen UV is when you pan the camera around or when you move the sprite around, you can see that the distortion goes really crazy. And the reason is that the distortion is based off of the sprite's location on the screen. So when I move the sprite location on the screen, the distortion gets changed as well, which is usually something we don't want. So the zooming in and out problem is something that's fairly easy to solve, but the distortion getting changed according to its location on the screen is something that's extremely complicated to solve. So for now, I'm gonna go back to the normal UV, which is a problem that's way easier to solve than what we had with screen UV. So our problem is that when we change the scale of the sprite, the noise texture changes as well because we are using the UV coordinates. So to understand it better, I want to be on a scale of 1 and 1, so it won't affect anything. And let's also zoom in to a zoom of exactly 100%. So this is the default size for the sprite. So when we look at the noise texture, it's fairly small, and by that I mean the ripples are fairly small. But what will happen if I'll scale it up? Let's say 5 times as big. Now we can see that the noise texture is 5 times as big as well, and that's something we don't want. I want to account for the scale of the sprite. So if we multiplied the scale by 5, we can multiply the UV by 5 as well. So now we have the same small size of ripples when the scale is big, and if the scale is small, we'll remove this multiplier to have the same scale of the noise texture. So our next step, naturally, is to make another uniform. So let's make a uniform. It's gonna be a vector 2, and we'll call it scale. And we're gonna multiply the UV by the scale value. And now when I change the scale, for example, by 5, we can change the scale right here to 5 and 5. And now it will be the same. Doesn't matter which scale I'm using. And if the scale is squished, and now our scale is not the same on the X and Y axis, we still can use this multiplier to account for that. So that's really good. Okay, you can stop screaming at your screen. You're correct. There is a way to automate this process. So let's add a script to our sprite and let's make it a tool so it will run in the editor, and I'm gonna use the process loop. So here I'm gonna go to the material, and to set the shader parameter, which parameter? The scale, and I'm gonna set it to the scale of the sprite. Now I'm gonna save, and I'm going to reload the scene so the tool will work. And now, even if I'll change the scale of the sprite and I'll try to stretch or squish it, you can see that the noise texture remains at the same proportions, which is exactly what we wanted. The problem is, right now it's pretty small, so if we'll multiply the UV and scale by something, it will change the constant size of the noise texture. So for example, let's multiply it by 0.5, and now the waves are bigger, even if we try to change the size of the sprite. One final problem that we need to solve is what's happening when we try to zoom in or zoom out. And we can see that the noise texture remains at the same size, but the amount doesn't account for us zooming out. So it remains the same even though we are zooming out, let's say 50%. The amount is supposed to be multiplied by 50% to remain the same. So there is a really simple way to solve this. We can just go to our offset vector and multiply it by 50%. And now it remains proportionate. Now I want you to pause the video and automate this process like we did with the scale. So that one was a little bit tricky, but let me demonstrate how I did it. So first of all, I'm creating a uniform. It's gonna be a vector 2 and I'm gonna call it zoom. And now I'm going to multiply the offset vector by zoom point y, which currently is 0. But now I want to set in the process function, I want to set the material to the current zoom of the game. And that's the tricky part. Let's create a var and call it zoom. And it's gonna be equal to get viewport and then global canvas transform dot y. And that will give us the zoom. And now I'm going to material, set shader parameter. The name of the parameter is zoom, and of course I'll give it the zoom variable. Let's save it and see what's going to happen. When I'll zoom out, we can see that the scale of the distortion remains the same, and when I zoom in, the same thing will happen. If something goes wrong, you can always go to the shader parameters and make sure that they are changing when you change the zoom or the scale. Now, unless the level is underwater, I don't want my water to be on top of the entire level. So what I'm doing in Prickle is just sending it back. And we have these pools, which are basically transparent, and you can see the water behind them. Just to be clear, we have two sprites for every hoglet. One is the sprite of the hoglet itself, and one is the water reflection, which is a child of the original sprite. And you can see that the water reflection is actually the hoglet drawn from below, and we use it on a Z index of -10. So it will be below the water shader and it won't appear on the ground. Finally, our water shader is complete and you can go celebrate. As always, if you have any question or if you need any help, feel free to leave a comment and I'll reply to each and every one of them. And of course, if you want more content like this, feel free to subscribe. If Prickle looks like something you'd enjoy playing, feel free to check it on Steam. I'll leave a link below.